Hi guys, welcome to Learning Electronics Repair. So today we're going to have a look at this interesting little project. This is on PCBWay.com and their shared projects. This is the area where you can upload your own projects, the schematics, the Gerber files, and if anybody wants to order the PCBs from PCBWay, either bare PCBs or already populated, you get 10% commission. So it's a great way to share projects, and that's what this guy has done. And I thought this was interesting. So this device basically is to work out the phase of a transformer. You'll often see on schematics these little dots. So basically it tells you if, for example, there's a dot at this end and a dot at this end, that when this end goes positive, this end goes positive. So that's what the dots actually are for. But I've never seen a device before that would actually take an unknown transformer and measure this for you. Sure, you could work this out with an oscilloscope, but this seems to be quite an easy little thing to play with, so let's try it. You can see we have a description of the device here, explaining it's important to know the transformer polarity sometimes, and there is a YouTube video, so let's take a quick look. And here it is. Let's see what the guy has to say. Yeah, go on.
Hey guys. In this video, I want to show you how to make an electronic circuit that helps you to find out the dot convention of any transformer.
As we were saying, so let's have a look at this. Yeah, he's building the project, he's explaining how this works. And here he's talking about the schematic. So what this basically does is he has a 555 time, and this is an oscillator, so this will be generating a square wave which is feeding into the primary of the transformer, and he's monitoring that with this OpAmp. So this will pick out basically whether the inverting input here is positive or negative in relation to the non-inverting input. This will give a square wave. And then we have another OpAmp on the secondary side doing the same thing. So the basic idea of this is whichever end of the coil has the dot, these will go positive at the same time. They feed into the inverting input on the OpAmp. So if the transformer is in this polarity, if you like, we'll get both of these going positive at the same time. If the dot was over here, then what would happen is this would go positive when this goes negative, and we'd get two square waves in anti-phase. So that's what this is doing. That's how it's detecting the phase. I can see that. And then basically feeds these into an XOR gate. So the XOR gate will give a high signal if either one or the other of the inputs are high. Okay. So if either this one is high or this one is high, this will go high. That will happen if the transformer is an antiphase, the secondary to primary. If they're both high together or both low together, that would happen if the transformer is in phase, then the output of this goes low. And he's using that to drive an LED, basically, or a couple of LEDs. There. Okay, so that's what he's doing, and that's how this works. You can see now how the square wave shown. So it's a very simple device, this, not much required to build it, just a XOR gate. Okay, you can see it there, LM358, and that's about it, a 555. So let's put this thing together and let's see how well it actually works.
See, the top LED lights up.
And hopefully it'll work something like this.
The primary and the secondary of the transformer winding in the same direction. So the input signal and the output signal are in phase. To prove that this circuit...
And as he shows you, you could actually do this with an oscilloscope. But let's build this thing and we'll see. And here are our PCBs from PCBWay.com. Already been opened actually, so I don't need the knife. Let's have a look. Yeah, these are very nicely made, as always with PCBWay. To be quite honest, the PCBs are very nice. These are 1.6mm, nice thick ones. You can have them in 1mm or other thicknesses if you prefer. All the components are marked, not the component number, but the value, so it's going to be easy to put this together. I'll fit some IC sockets. It just helps if things go wrong, basically. You can easily change parts if you manage to actually damage something. Well, hopefully this will go quite nicely. These are the connections for the terminals that you connect your leads to, and these are your LEDs. So I'll put this together. I'm sure you know how to do that, so I won't have you suffer watching through that. And then let's try it. I've constructed the device. You'll notice there's some capacitors here and one here. So I had a bit of a problem with this PCB. It wasn't really a major problem, but for some reason the footprints for the capacitors were too small to fit them. In particular, I couldn't get the legs through the holes. They were all like this one here. You see it's very small. So what I've done is this connector here, if we look down the edge there, it says 3 volts, okay? And I fitted the capacitor there. It's actually these 2 holes are directly wired to those, so the capacitor is directly across the input voltage, and in fact that's what it shows on the schematic. So I've done that by mounting the capacitor here instead of here, then it fitted in. So you can see this is like a normal footprint for a capacitor, and these are very small. But if you look at the guy's video, he actually managed to get the capacitors in there. Yeah, you can see it here. So if you look, this actually says 5 volts, but on my board it says 3 volts. I'm going to use 5 volts. He's got the capacitors in there, but I'm not sure the PCB is exactly the same as mine. At least that is different, so maybe the footprints are a bit different. I also didn't have any more banana sockets. I've used what I had. I'll order some more, so I just soldered some wires on, and you can see that there. So the wires are tagged on, just a temporary fix if you like, so we can get this working. The same with the switch, it wouldn't go through the board, but it's there. So I'm going to put 5 volts in this, although it says 3. These capacitors, it doesn't mention the voltage on the parts list for this, but the actual capacitors are wired directly across these LEDs. That's because basically when the LED lights up one or the other, it's actually pulsing with a square wave, so that effectively smooths it out and illuminates the LED steadily. So that's what we have. So let's power this up and see what happens. I'm going to use 5 volts, and I expect nothing will happen at first. Power's on, press the button. Yeah, you expect nothing to happen because there's no transformer attached. So let's attach a transformer. So this is off an old ATX power supply, a scrap one. We can see there's a primary, so I'm going to come across here and here. Looks like this might have had a center tap, but I'm not too bothered or interested in that. These are 2 pins that are actually attached to the PCB. So we'll come in here. Now with these are secondaries. This is the end of all the secondaries, and these are separate. So we just need to find a secondary we can use. I suspect we can actually use any of them because they'll all come to here. Let's just get the test meter and prove that. Quite often with these you'll have ones which are tapped, so the same winding gives a 3.3 and the 5, and then you have another winding for the 12. Let's have a look. So if we measure from here, just an ohms range, that's pretty much short. So these are on the same winding, 1, 2, 3, 4, 5. So they're all showing the same because they're all connected together here, okay? Which one read the highest? That one. So let's go from here to this one and use a secondary as an output. So we'll put from the output, doesn't really matter which way round, green, white, okay, and then on the input, white, green, okay. Connect the power again. This is just the power we just fell off. And let's see what it does. So we'll push the button. Nothing happens, okay. So let's make some basic checks. So first is, do we have power? Okay, so there's power on the board. Let's see then what the problem is. Okay, so here's the schematic. So the first thing we want to find out is the NE555 chip oscillating? So we can go on pin 3 of the chip, and then we have this 100 ohm resistor which goes to pin 3 on the op amp. Let's have a look. So we want to look on pin 3 here, and we want to have a look at pin 3 and pin 2 on the op amp. Okay, well, using an oscilloscope, that was without doubt the easiest way to find out if it's oscillating, and I have no idea what frequency it's actually running at, so let's have a look. Let's see. So we have the oscilloscope there, you can see it. I have the ground lead of the scope probe connected to the ground on the power supply. So NE555, which is this bottom one, pin 3. Okay, press the button and it oscillates. Yeah, you can see that quite clearly. Yeah. What frequency do we have? Not that it really matters, but out of interest. Okay, so it's definitely driving the transformer. What comes in on pins 2 and 3 on the op amp? Let's have a look. So pin 3, yeah, that's the oscillation there. Pin 2 is effectively not doing anything. So pin 1 should be the output of this. What do we have? Well, pin 1 seems to be just high. Let's adjust the sensitivity of the scope a little bit. 2 volts per division. Let's see. There we go. Yeah, 3, 2. So 2 is effectively just hovering around there. 1 has a little bit of a signal on it. Okay, nothing much. Let's have a look. Yeah. Well, but there's nothing much coming out of this. Okay, there's nothing much coming out of here. What's coming out on pin 7? So this is your other op amp. This is on the secondary of the transformer. So you can see that this point here, with the two 100k resistors, should be at half supply voltage. So if this is 5 volts, this should be 2.5 on here. Okay, and we should have a signal coming through the transformer on here. The 2 diodes will prevent the signal going more than about 0.5 or 0.6 volts in either direction, but that's plenty enough to switch an op amp, and we should have a signal out on 7. Let's have a look. So 5 has the waveform on, 6 is the one that is at about 2.5 volts. No, in fact they both have the waveform on. Okay, 7. So 7 has a waveform. So basically the signal from the secondary is coming through. We don't have anything on the primary side. Just referring back to the schematic again. So pin 2 is connected to ground. Okay, pin 3 has the waveform coming through the 100 ohm resistor, which also drives the transformer coil. We know it's driving the transformer coil because we have a signal on the secondary square wave, so we know that's working. We know this is switching here. So the problem appears to be the output of this op amp. It's not really changing very much. Now that could be a problem with this chip. Yeah, if you like dragging that down, could be a problem with the op amp. So what I'll do is I'll take this chip out, and let's see then if we see any sort of signal on pin 1 here. Okay, because as we can see, I'll just demonstrate what we were looking at. Pin 2 goes to ground. You notice that's floating high normally. That's because this switch connects to ground. You'll see the same thing happen on pin 4 of the chip, which is ground. So that is normally just floating. Look at 5 volts. Yeah, this is floating at 5 volts. And then the ground goes to ground. So that's how it switches the power. So pin 2 goes to ground. Pin 3 gets the square wave, which is going above ground, so that should switch the output of this high-low. And well, you can see what it's doing. Yeah, you can see what it's doing. It's there, but there's a problem. Compared to this one, which is working. Let's take the CMOS chip out. Okay. Try again. So, if this still has a square wave on, which it does, then pin 1 should also have a square wave on, because they both drive that. It looks like this op-amp's got a problem to me. Let's change the op-amp. Okay. Go again. Pin 7, switching. Pin 1, not switching. Well guys, after some messing around, I eventually figured out why this doesn't work. So the problem is, if you look at the circuit here, the inverting input of the op-amp is connected to ground. Okay, so for the output to switch here, the non-inverting input would have to go below ground. It would have to be negative on here. Okay, so this would actually have to be going positive and negative. Now we have an inductor here, and if I actually look on the oscilloscope, and I've shown you guys here, it does actually look like the signal here is going positive and negative symmetrically, roughly around 0. And I do have it set onto DC, not AC. But it seemed to me that the reason this can't effectively work is because the non-inverting input is always higher than the inverting input. That's why the output was always high. I had like a little bit of a trace of a square wave on, but tiny. So I thought to test this, the best way would be to actually put a voltage on here, not ground. Okay, actually to increase the voltage here a little bit. So just as a quick test, what I actually have done is just taken pin 2 out of the IC socket, so it's just floating at the moment. It's just floating. I want to show you now what this actually does. You'll also see, by the way, I've fitted another switch. I was having trouble getting the wires through these holes. The one that's soldered directly on the board came away. It wasn't making a very reliable contact, so I did this, and the other white wire is just attached to here, which actually goes to there anyway. So this is the device as it stands. At the moment you'll see that the pin 2 is floating. Now let me show you what it does. I'll switch it on and we'll press the power button. And you'll see one light is lighting up bright and the other one's actually lighting up dim. So I have one LED lit up bright and it's the top one. Okay, so what this should indicate is that this lead, the white lead, this end of the transformer winding, is in phase with this end. Okay, just zoom out a little bit so you can see the transformer winding. So what I'm going to do now is I'm going to reverse the polarity on the secondary. Okay, so we'll put the wires the other way round. And let's try it again. And now you'll see it's not quite so obvious. The bottom LED it's brighter, but what should happen is just one lights up. Yeah, so it's not giving a very good indication. I hope you can see this is brighter. Let's have a look at the waveform. So the waveform is coming out on here at pin 10, okay? You can see that on the schematic here, so pin 10. If we just move the scope away from that a little bit, you see it goes to the junction between the two LEDs. So if this is low, then this LED will come on, and if it's high, this LED will come on. This will be low if both inputs are the same, either both high or both low, because it's an exclusive OR. And that will happen if these two signals are in phase, okay? If one is high and the other one is low, so they're out of phase, then the output will go high and this LED will come on. So let's have a look at what we can see on pin 10. Okay, so this is pin 10 of the chip. And you can see it's basically high. It's about 5 volts according to my scope. If I push the button, you'll see we have a square wave more high than it is low, okay? And if I swap the polarity, it's now more low than it is high. Can you see that? Okay, so it is basically working with the pin 2 floating on here, but that's not very good. So what I'm going to do is I'm going to connect a variable resistor with the wiper connected to the pin 2 and connecting between ground and VCC 5 volts, so I can actually vary the voltage on here myself. So let's do that and see what happens. Okay, so I've attached a potentiometer. The black lead is ground, the red is going to 5 volts. I just found somewhere I could tag it on, and the blue wire is going to pin 2. So I can now vary the voltage on pin 2. Okay, we can just test that if we just get the scope. So we can see that has 5 volts on it. I'll have to press the on off switch. It's now going to ground. Let's just turn the potentiometer the other way, and it's now staying at 5. Okay, so if I go somewhere in between, we get the square wave. Okay, so if we now look at the device, that's actually working. So it's lighting up one LED, and I've just set a voltage that suits this basically. Why I'm seeing a square wave, I'm not totally sure. I thought I would see a DC level on here, but in fact I don't. I see a square wave. Okay, that's very interesting. I need to think about why that is, because this end of the potentiometer is ground. Okay, this end of the potentiometer is 5 volts, but on here, pin 2, I have a square wave. Yeah, that's interesting. Pin 1 now has a square wave, pin 7 has a square wave. So, that's interesting. It can't be these diodes, because I have pin 2 sticking out into the air. I just have a potentiometer just to put a voltage on there. But by some bit of magic, this actually seems to work. I just don't quite see why I get a square wave there. Guys, why has that got a square wave on it? Comments. In fact, I'll ask my friend Det, because he's coming in a moment, and Det wants to have a quick chat anyway about this particular circuit and how we may be able to improve it, yeah? You can see, look, pin 2 is completely floating in the air. It's connected to nothing but the centre pin on our potentiometer. Let's see if this actually works correctly, so it lights the other LED if we reverse the polarity. So we'll reverse the polarity on the secondary. Okay, what happens now? Yeah, it works. I guess we still see a square wave on pin 2. Yeah. Okay, well, you guys comment and let's see what Det thinks as well. And we'll have a quick chat about how we could improve this. Or is it possible to improve something that works? Hi guys, so I have Det with me here. We just looked at this little problem. So I'll show you with the scope just to show nothing stupid is going on here. We just go to the thing. Now,
yeah, just to let you know, this isn't scripted. We're just talking about this.
We're just talking about this.
Really, two guys trying to wrap their heads around.
Because we don't really know. So this is 5 volts, okay?
This is a frozen picture, I think, from your scope.
Oh, so it is. What?
Yeah, people. Yeah, this is live.
This is live. Yeah, this is live. It obviously doesn't like you sitting close to it.
Oh yeah, it's me again. I'm always responsible.
It's no longer frozen. Okay, you can see it's live, guys. So if I go onto the 5 volts here, yeah,
there's 5 volts. This is fine.
And if I push the switch, this is 5 volts.
This is what we expect. Yeah, 5 volt doesn't budge.
I move my meter lead out the way; it's stuck in somewhere. And if I go onto the black wire, this is ground.
Fat ground. Okay.
Let me just get a connection on it.
Oh yeah. And since you're switching the ground plane,
when you switch to the ground plane, it goes down to 0 because we switch in ground. Yeah.
Yeah. So that you can do this. This schematic, from a schematic point of view, this doesn't make any difference.
And pin 2, guys, look, it is floating in the air. Yeah. It's not attached to anything on this PCB other than the blue wire on the pot. And we go on here,
flapping in the breeze, you know,
flapping in the breeze, and we have a square wave. Now, I said, because we said, how can this happen? I mean, the inputs are high impedance. Now, I was saying with Det, and you guys can follow this along. So, I'm saying with Det that effectively with an OpAmp, it always tries to balance the inputs so they're the same. But normally you have a feedback resistor in here.
You must have. Yeah, this is how you push against the input current. This is why you have the pushing that.
So if there's no feedback resistor, how can it affect the voltage on the other input? It can't. So is there something internal in the OpAmp that makes it do this?
I'm sticking with this can't be because the inputs are always high Z. These OpAmps are designed to have non-impact on the whatever you're measuring, and it doesn't matter if the input is simply floating in the air, flapping in the breeze. You don't have any. This resistance over there must be in the mega ohms.
It must be, yeah.
And there is no output on an input on an op-amp.
No, I know. And also, these diodes are not connected to the op-amp anymore because the pin 2 is floating. It's not floating, it's on the potentiometer.
You know what? Do you have a whole charge of defective LM358s?
I don't think it's faulty because it actually works. So, guys, what do you think? Now, what we will just prove, and we were just looking at this, and then we want to talk about the circuit because Det has quite a few interesting points, so more stuff we can discuss. But if we just go back to it, so you'll see that when I have the transformer in the phase it's in now, the top LED is lit and the bottom one is out. Okay? So that's saying that whichever pin the white clip is going to is in phase with that one. They're in phase. Okay? Now if we go the other way around, green on here, reverse the phase on the secondary, the other LED lights up. But you'll probably notice this one's lighting up dimly. Now that's telling you that this end is in phase with the dot. Okay.
Does it make any difference at this point if you turn the knob? Or
well, this is exactly what I'm interested in. I only have so many hands. So
okay, yeah. So I'll do the
yeah. So let's press the button. So you can see the LEDs now. Just adjust it a little bit.
Okay. Moving. There's nothing happening. I'm moving. Oh, but you have to go really far. And then I can't get the other LED to turn off.
No. This one should be on. So even if you turn the thing further down,
okay,
this is always on dim. Yeah.
We need even more hands. I think we need. Wait, I can hold the power switch, and you measure what's on. Let's see what's on the scope on pin 2.
Have you noticed though that this one actually doesn't come on straight away? Dim. Watch.
Yeah. I saw this. This is a cap.
Like something's charging. Oh yes, there's an electrolytic.
These are the caps across the LEDs.
Yeah, that's it. Yeah.
Let me press a button and you measure what's on pin 2 while I turn the pot. You can do.
I can do so. The scope probe on here.
All right.
There's your square wave.
All right. Oh.
It's just adjusting the amplitude of it.
But how do we adjust? This looks like a... No way.
Way.
Look, this looks like you adjust... This is just really adjusting the amplitude.
Yeah, way.
But this would be, if you don't have to connect the upper side of the pot to 5 volts, this would be like you connected to the output of something. Yeah.
Exactly, yeah. But it is now working.
You didn't. We measured this.
Yeah, we measured that.
Sorry,
we measured 5 volts and we measured ground on the scope. There's no square wave on the 5 volts. So it definitely works, and the potentiometer position doesn't seem to have a great deal of effect.
Yeah.
So we just go the other way again, and we just make sure it's still working on this one.
Oh yeah, you have to connect this. Yeah.
Yeah, the other one lights up.
Yeah, this works.
So it works. So guys, what's to talk about there? What's happening there? I'm sure somebody, you know, yeah? You know. But, Jack, you want to talk about this device and this circuit, about the layout of the PCB, wasn't it?
Yeah, I really love this circuit, by the way. So, who's the guy? Musa from Simple Project. Good job, man. Good job. Nice PCB.
Yeah, his name's Musa, yeah?
Yeah. I have a few suggestions here, and
Okay.
Richard got the PCB from PCBWay from the project thing.
Yeah, shared project.
Yeah, shared project. And I tried to look where are the Gerbers because I wanted to see the traces here, and there were no Gerbers.
No.
And when you download something from the project page on PCBWay, you don't get Gerbers because this is all handled internally.
This is down to the author. So when the author uploads a project, he can upload whatever he wishes. So, for example, the projects that we shared, we upload the zip file that contained the schematic, the Gerber,
and the ID,
and the BOM.
Yeah.
But that's down to the author.
Yeah, I know. But in the process with PCBWay, I can't extract somewhere with a magic thing.
Yeah.
I can't extract the Gerbers, so I don't have an idea. This PCB, you see this on screen there in big. You can't tell where the traces are. This is a big downside because I wanted to follow the traces here because I wanted to see, is this right?
Okay, so we could actually ask PCBWay to make them in a different colour. So we could do that. My issue with this, by the way, is you can see the holes for these capacitors are too small, the footprints are wrong. And the fact, this business of it not working until we added the potentiometer, this may well be very much related to the type of transformer.
Oh, yeah.
So I know, Musa, on your video, you had it working without this, but it seems to us that you have to do this and maybe have to adjust it depending on the type of transformer.
Yeah, we were trying around there. We were really faffing around because we ran out of ideas because I think the circuit must work. Maybe it's really the transformer. I don't know. My analog foo is probably not good enough for that. But I have a few more quirks in here, but these are details. And I'm not Robert Fennick. If Robert Fennick would be here, he probably would find some more. He's a guy who does layout as a form of art. He's really good with that.
Okay.
What I saw from layout, this looks like an auto route, and this looks like really, really tiny traces that go everywhere. Well, you can do that, but then you do a flood fill, and you keep all the copper that you can keep on the board, because elsewhere the copper goes right into the etching solution.
Yeah.
Not good for the environment. Do flood fills.
Okay.
Every time.
Okay, makes sense.
Yeah. What I don't like is the you mentioned the little holes in for other components. This is bad design. Maybe the footprints were simply bad that he used. But if you have problems fitting in a cap here down there, we have the orange caps down on the bottom screen. They didn't fit through the holes.
These ones. They wouldn't fit.
Yeah. And you have so much space on this board, so you could have used a footprint that has big holes. This is normally a step I do between having everything laid out, and then I do a check: how big are my parts? Do I have space left? If I have space left, I simply extend the parts, because this makes life easier to. This makes life simply easier to solder. This is a beginner's project, so you want to make this easy.
Okay, so anything else about
one more?
Sure, fire away. Continue, my friend.
Yeah. I don't like the footprints you use for the resistors. Look at this, how small they are. So you have to fold the resistors right on top of the resistor. I know this is very not so important, but I'd normally say leave a bit of wire there so you don't stress the resistor mechanically. So I'd use a tiny bit longer.
A little bit more space.
More space, and the space is there. So if you'd use the footprint, it's a bit longer, so you have more space to place the resistors.
It's actually true, because I had some 4-band resistors and 5-band, and the 4-band ones wouldn't fit in.
Yeah.
They were too big.
I'd say these are maybe not for 1/4 watt, but for 8 watt.
Something like that.
Yeah, so the smaller ones. They are available in tiny packages, but yeah, not so great.
Okay, so can I put you on the spot, Dad?
Please do.
Okay, so let's go back over to this. This is the actual device. I'll just get rid of the scope now. We don't need the scope anymore. Okay, so what we have here, we have an oscillator square wave.
Yeah.
Driving the primary. These diodes just limit the voltage to plus or minus 0.6. Although I've actually disabled this at the moment.
Yeah, indeed, you did.
On this one, yeah. That's probably not a problem, because this is the primary. You don't know what the secondary is going to be giving you. So plus or minus 0.6. And we have 2 op-amps, and they either give us square waved in phase or anti-phase.
Yeah. Okay, that's why we need to accept.
So that's it, and that works like this. Could we replace this with a single microcontroller that oscillates? We'd probably still need the op-amps, or could we just use analog inputs like ATDC? And then could the microcontroller figure out if the 2 square waves are in phase or anti-phase and just light an LED?
This is not scripted. He just hit me with that.
I know. I did say I'm going to put you on the spot. And would it be better with the double op-amp and a microcontroller? Could the microcontroller just do this?
Since we're clamping the voltage, voltage on the analog inputs will never rise above, say, 0.6.
Yep, correct.
Never. It can't rise higher because of the diodes.
Yep.
So there's not a really problem, because on the primaries it's pretty easy. I can't point here. Let me steal your mouse. Yeah, let me steal your mouse.
Yeah, that's good.
So we could grab this one in software. Thinking in software here.
This is your square wave input, so you know the phase.
We don't need to measure this, because we already know where we are on the.
Well, in fact, you would be generating this with the microcontroller and sending it into the transformer primary.
What we have to check, 555 is pretty beefy when it comes to output currents. Okay. A microcontroller, not so much.
Maybe a MOSFET then?
Yeah, I'd say let's drop in a MOSFET. Okay. This would be still less components.
Oh, yes?
Yeah. Drop in a MOSFET and let the MOSFET pulse the transformer. Yeah. We don't need stage 1, because we know where the phase is.
Because we're generating it.
We're generating it.
Yeah, okay, great.
And then we grab the output, and we need to clamp this down. So this is what this thing does. This fits it somewhere in the middle of VCC. Yep. So it's swimming around VCC, and then we have to try if we're fast enough with the ADC in there. Well, if the ADC runs fast enough, this should be doable. What kind of frequency are we generating?
Do you know,
right now?
actually, I didn't even measure that, but it's not very high, I don't think. But even if like the ADC is a little bit slow, can we kind of figure out whether they're in phase 90% of the time or out of phase 90% of the time?
I'm just thinking,
something like that.
I'm just thinking if we maybe do a signal forming, but I want to keep the component count low. Of course, I will.
I'm thinking 1 microcontroller, 1 MOSFET.
Yeah, one mic, 1 MOSFET. Yeah, and some LEDs, of course.
Yeah, or a bicolor LED. Oh, yeah, some LEDs.
Yeah, bicolor LEDs, something around there. Yeah. This would be, this must be tested. Yeah, this is something we have to test out and figure out if this is workable. Well, component count wise, I'd say we are on the plus side here, because we're eliminating 3 chips and replacing them with 1. Yep. We don't need a bunch of resistors. No. We probably won't need the totem pole with the LEDs over there, because we can do this anti-parallel. So exactly. Yeah. And so, you want to try this?
Well, this is it. First of all, would you like to try it? Yeah. And if so,
you know what? These people out there, they should tell us.
You guys, what do you think? Do you want to see it?
Yeah, they should tell us, because if they want to see this, we try to do this, and we try to do this step by step, so you get all the nasty bits when we're sitting around cursing, drinking beer.
Yeah. It's usually the case. Okay, so thanks, Det, for joining me on this one.
I have some more quirks.
Oh, sorry. We'll cut that bit out there. We said this was not scripted, guys. Carry on. I will not button until you finish. Go on.
Leave this in there. What I talked before was hardware on the PCB. I have some quirks with the circuit itself. For once, this is nasty because he never included some caps around the chips.
Decoupling caps on the power rails.
Decouplings, yeah. So for the MOS chip, the what was it, 4030?
4030, CD4030 CMOS.
You need a decoupling. These are normally the 100 nanofarad you find everywhere.
Okay.
Yeah, and 100 nano is fine. It will work. It probably will work on this board because it's a battery. A battery is the most stable, the less noisy power supply you can get. Yeah. And it probably will work without.
There is, by the way, not shown on the schematic, but there is a 250 microfarad directly across VCC to ground on the PCB.
But this is input, and you normally put them around the chips. You do this.
Yeah.
And I'd say this is good practice. People, if you're designing boards, don't cheap out on these caps.
Yeah.
If it's something digital in here and you got some frequency wobbling around everywhere, this keeps the supply voltage clean. Yeah. And it doesn't cost anything. It's a bit more complicated on the layout than, but please include them. This is good practice. Yeah. If you get used to this, to include these, you never forget this. Yeah. You simply throw them on here, okay, I need my teacup cap, so boom, 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 and you're done.
Oh, actually, and that reminds me, so something else we discovered with this circuit is that this XOR is actually a quad XOR.
Oh, yeah. We talked about
it. Yeah. So this is you guys again, what do you think? So there's 4 of them. Yeah. So the other 3, what the guy has done is he's connected both inputs together. So they are floating, but they're both connected to each other. So like on the other gates, both inputs are connected together. Now, Det was saying you should connect them to ground. Both. Always. And I said, but Det, this is an XOR gate. So if they're both floating, with an XOR, whether both inputs are 0 or both inputs are 1, the output will always be 0. So connecting the 2 of them together means the inputs will always be the same. So the output will always be 0, regardless of what they float to. Yeah. And we had a big debate about this. And Det basically said, yes, I'll give you that one, you're right. But he then said, but it's such good practice to ground them, you should always do it anyway, rather than trying to be clever and thinking why you didn't need to. So, guys, what do you think? Should they be grounded, or because of what I said, does it not matter?
Let me add to this.
Okay.
What I normally say, if you have a logic chips and there are inputs that don't do anything, because in this 4030 chip there are 4.
And we're only using 1.
And so we're only using 1. So you have a generator on there. The 555 is generating some frequencies, so this will be pulsing and some RF interference there. And if they leave them open, your chip can start to oscillate. And this could be really bad. So you start your chip and you're wondering, what's drawing half an amp here?
Yeah.
It's an XOR just burning away, and you have no clue where it's coming from. With the XOR, Rich is right. Yeah. With the XOR, you probably get away with simply...
It can't oscillate.
It can't, because you need different inputs there.
Yeah.
But again, good practice. This is again good practice.
Exactly.
If you have an input you don't need, ground it.
Yeah.
No discussion. This doesn't make your layout more complicated, because it's a layout. This is not a bridge you have to do on your board somewhere.
Yeah. So you can see, guys, we had quite a discussion on this one. We both think we're both right, but Det's really right. We just listen to Det here.
From the master himself. I feel honored.
Well, is that it then?
Let me look. Yeah, that's it.
Okay, so
again, Musa, please don't be offended, please. This is great that you're doing that. We checked your webpage, and I thought, man, this guy is really busy, and I'm but I'm lazy that well.
Okay.
Great little project. Give us a Gerbers if you do this. Make this complete. Don't stop at the probably people won't need this. The schematic is nice, of course, but I would like to have my Gerbers. I like to track my tracks and be sure that everything works. Where did this go? What are you doing there?
It looks like the video started playing by itself.
Oh, this is a video. Yeah. Okay.
Yeah, it was on pause. There we go.
Yeah.
Okay.
Whoa, interesting.
Well, that's just what we wanted to end with. PCBWay.
PCBWay.
Hey, PCBWay. So. Actually, I was honoured also, and we all were, by having Det along today, so thank you very much, Det.
Thank you, mate. I'll let you do the outro. I simply roll out of
We're finished.
Special effects.
What else can I? Special effects. No expense spared. Okay, and special thanks then to PCBWay for making all this possible, and to you guys for watching, which also makes it possible. Ciao for now. Bye, nerds.